Hi. Okay, so we're going to start this afternoon's sessions. We've got some very interesting talks this afternoon about stellar mass compact objects. And we're going to start the afternoon with a review talk by Michela Mapelli, who's going to talk to us about the formation and merger rate of binary compact objects.
Thank you, Natalie. Am I audible? So, good afternoon. First of all, I'd like to thank the organizers for inviting me to this exciting conference and fantastic location. So this talk will be a review talk about the formation and the merger rate of binary compact objects. So the topic is a bit broad, actually it's crazy broad, which has two implications. Number one, Abbas Askar will be giving another review talk after mine. So we decided to split this, and I will not touch upon the dynamical formation channel. Abbas will focus on that. It is very difficult for me because dynamics is super close to my heart, but we had to split one way or another. So I love dynamics, but I will not talk about it. But you can ask me questions if you want. Second disclaimer is the topic is so broad that I will not be able to discuss every recent or not so recent, super interesting result that was published in this field. Please don't be upset if you don't find some paper you like in my review, but we can, of course, I will be happy to discuss about it in the Q&A or later on in the discussion. So now okay, the outline of the talk. I will first give a very short overview of some results from gravitational wave data. Then I will focus on the formation of binary compact objects, especially the open questions and the things that do not work. Then the merger rate density, the host galaxies, and I will summarize. So Architman, in his great introduction yesterday to gravitational wave results, has briefly showed this plot. So this shows the merger rate density per unit primary mass and time and volume as a function of the primary black hole mass, the mass of the black hole that is the most massive one of the two that merge in the LIGO Virgo data. And this shows, these different lines show the intrinsic distribution of the primary black hole mass that we can infer from gravitational wave data after accounting for selection effects, for observational biases. Moreover, each of these different lines is a parametric or non-parametric model. So it is a fit to a parametric and non-parametric model, which means it also depends on the model. But reassuringly, the different lines retrieve more or less the same features, the same structures in the black hole mass function, which are a primary peak at around 8 to 10 solar masses, a secondary peak at around 35 solar masses, and then a high mass tail extending up to 80 or even more solar masses. And then there are also other possible features according to some of the models, but these are still consistent with stochastic fluctuations. So clearly, these features encode information about the formation of these objects, of binary compact objects, binary black holes in this case. And most of my talk will be about how we can dig this information out of these structures. And then there is also another very important quantity that we can infer. If we now marginalize over the masses, we get the merger rate density. So in this case, it's number of mergers per unit volume per unit time, which is the blue line with the 50% and 90% credible interval shown by the shaded areas. And we see that with the results that we have now, this I should have said it before, is GWTC3, the third gravitational wave transient catalog. So this is up to the third observing run. You can see from this line that the merger rate density is increasing with redshift. So it's not consistent with uniform incomoving volume. And this is also telling us something very important, and I will try to discuss what we can learn about this and how can we use this to interpret the models that do not work. So let me start now from the basics of the formation of binary compact objects from massive binary stars, what we know about it, and then I will move on to what we don't know. So we expect neutron stars and black holes to form from the collapse of massive stars. And especially the most massive stars, the black hole progenitors, lose mass during their life via stellar winds. For many years, for many decades, we have known that the mass loss rate depends on the metallicity of the star. The higher the metallicity, the higher the mass loss rate, as you can see from this plot on the left. But over the last few years, we are learning, we started to realize that also the luminosity of the star is a key quantity, especially for the most massive, very massive stars. And namely, the closer a star is to its Eddington luminosity, the higher the mass loss, almost regardless of the metallicity, because then the mass loss comes mainly from Eddington scattering, from Thomson scattering. And this is shown by these, for instance, new results by Sabait and collaborators. So the final mass of the progenitor star is a key quantity to interpret the final fate of the star, the collapse. And when we want to study the outcome of a core collapse, as Matteo also mentioned this morning, the key point, the fundamental question is, does this specific star, stellar model, will end its life with a successful supernova or with a collapse, with a direct collapse? And if we find out that the answer is yes, then the remnant will be either a small neutron star or a low mass black hole, less than 3-5 solar masses. If we find out, and for this we really need hydrodynamical simulations of core collapse, that the supernova is not successful, then we expect a direct collapse to a black hole. And then the black hole can be massive. It can accrete most of the mass of the star. And the general idea, but it may still be wrong, the general idea is that since metal poor stars, if they are not radiation pressure dominated, they tend to end their life with larger pre-supernova masses than metal-rich stars, then they may be more likely to collapse to a black hole directly and produce a more massive black hole. So this is the general idea, but there are many things that challenge this idea. Number one, per-instability supernova. If a star is very massive and metal poor, at the end of carbon burning, it may efficiently produce electron and positron pairs nearly at rest in its core. And this softens the equation of state of the star, of the stellar core, and may trigger an instability that we call per-instability, which has a variety of important effects for astrophysics. But here I will just focus on the main consequence that it may have for compact objects, especially for black holes, which is we expect per-instability to open a gap in the mass function of black holes somewhere. Historically, people assumed that this mass gap is between about 60 solar masses and 120 solar masses. And here you see the mass gap and other features in this plot. This is a model for the expected mass of the compact object as a function of the initial mass of the star for different metallicities shown by the different lines. This is a quite old model, but let me first discuss its feature, and then we will see what are the uncertainties. So here on the left, for stars below 60 solar masses, we see the trend that I mentioned before. The lower the metallicity of the progenitor, the higher the mass of the black hole. But then for more massive stars, the plot becomes quite more complicated. There are regions where we expect no mass of the remnant at all, so no compact object at all. This is where instability triggers a disruptive supernova that leaves no compact object, and this depends on the metallicity. But then there are also regions where the star develops instability, but then it loses mass through pulsations and then forms a black hole, although not as massive as it would have done without the instability supernova. And then we may even have some very massive, very metal poor star that collapse directly and leave an intermediate mass black hole. So the situation is pretty complicated. And in the last few years, several groups have intensely investigated the problem of instability supernova. Here you see just some of the interesting papers that were published, mostly triggered by 1905-21, the LIGO Virgo event with the primary mass in the instability mass gap. And all of these studies have shown how large are the uncertainties about the mass gap boundaries. Let me just show you two of the many plots that I could have mentioned here to highlight these uncertainties. So here you see both of them are models. So this is the mass of the black hole that we expect as a function of the 0H main sequence mass. So this is the same as before, but now we fix the metallicity, and there are different colors. The different colors correspond to assuming different values for the carbon alpha nuclear reaction rate, this reaction that produces oxygen in the core of massive stars. And you see that by changing the rate from -3 to +3 sigma, the maximum mass of the black hole below the instability mass gap can change from 110 solar masses down to 70 solar masses. Moreover, here you have two lines, the solid and the dotted. The solid shows the most optimistic case in which you assume that if there is any residual hydrogen-rich envelope bound to the star, this will collapse while the rest of the star collapses and will end up accreted by the black hole. The dotted line instead is the most pessimistic case in which only the helium core can collapse and produce the black hole. And the difference between the two lines is pretty large, and it depends on the actual energetics of the failed supernova and the binding energy of the envelope. Here in this other plot, you see how the threshold for instability is sensitive to the assumed stellar wind model. It shows the metallicity, the 0H main sequence mass of the progenitor. And this black line here shows what was the threshold a few years ago, what was the best threshold for switching on instability. So above this metallicity, you cannot have instabilities. Below, you do have instabilities. While the white line shows the result for this very same threshold if we assume new stellar winds model that fully account for the Thomson scattering. And you see that there is a huge difference. So this is to give you an idea of the uncertainties. But the situation is even more complicated because LIGO and Virgo do not observe single stars that produce single compact object, which is what I focused on in my previous slides. LIGO and Virgo observe binary compact objects, and binary compact objects may form dynamically, Abbas will talk about it, or they may form through the evolution of a massive binary star. And when two stars evolve in a tight binary system, several other processes kick in that are barely understood. I will just mention mass transfer. The two stars can exchange mass to each other. This leads to the removal, maybe a complete removal of the envelope of the donor. They may also trigger, mass transfer episodes can also trigger collisions between stars that produce very exotic objects. Abbas will also mention these. Or they can lead to unstable mass transfer, which means mostly, but not only, a common envelope phase. And if you want to know more about the details of mass transfer and the problems of common envelope, you can check these two recent reviews. So all these ingredients will affect the mass function of the black holes that merge and that we can observe with LIGO and Virgo. And I will first now show what we expect from the standard model. Then I will discuss what are the problems, some of the problems of these standard models. And for the standard model, I will use my models, so I will take the blame. This plot shows the number of binary black hole mergers that we expect from binary population synthesis models as a function of the primary black hole mass. Binary population synthesis means that you simulate massive binary stars from their zero H-man sequence until they form binary compact objects, and these compact objects possibly merge. And population synthesis means that the models are very fast. So the simulations are very fast, although sometimes not completely accurate. And the different lines show different metallicities. This plot is the same on the x-axis. The x-axis is the same as I showed you before, the LIGO-Virgo plot, but in this case, is theoretical models. And you see that there are several peaks here. A peak at about 8 solar masses that comes from high metallicity, relatively high metallicity binaries. This is mostly because of the assumed core collapse supernova model. Then a secondary peak that pops up at low metallicities at around 35 solar masses. And this is mostly connected with the direct collapse and with the maximum mass of a black hole in the evolution of a tight binary system. But then there are also other features. So for instance, a possible peak here and a sharp drop at about 50 solar masses. This is not the maximum black hole mass in this model, because the maximum black hole mass in this model from a single star evolution is around 65, 70 solar masses. So the difference here is connected with the removal of the envelope during mass transfer. When two stars exchange mass to each other, the envelope can be completely removed, and then the maximum mass of the black holes will be lower. And then you may see also the difference in the efficiency of binary black hole formation from the metal-rich to the metal-poor progenitors. So let's now compare by hand with the data. We have a peak here that is also suggested by the LIGO and Virgo data. We have a peak here that is also suggested by the LIGO and Virgo data. Problem solved. Is metallicity the origin of the LVK peaks? Maybe. I would be happy if it is. But it may be a coincidence because of the uncertainties about core collapse and peri-instability supernovae I briefly discussed. The uncertainties on mass transfer, I will come to that in a few minutes. Uncertainties on stellar rotation. And the problems that we have with the merger rate. Plus, what happens here? Where are the high mass black holes in the models? Well, an option is that dynamics provide the high mass systems, and Abbas will tell us more about this in his talk. Now, let's point out a few problems, more problems. Mass transfer. It is very difficult. It is quite unrealistic to expect that the process of mass transfer is always conservative. If mass is lost, then also angular momentum is lost. And there are many possible options for the angular momentum loss. Angular momentum may be lost from the accreting disk or from a circumbinary disk around the binary system, or from the surface of the donor star. And each of these three scenarios has very different outcomes. In the default of population synthesis simulations is this one, is the isotropic re-emission. What about more accurate models? There are very few hydrodynamical models of mass transfer. And these models by Morgan McLeod and collaborators show us that the loss of mass and angular momentum is most likely to happen from the second Lagrangian point, from L2, which is more similar to this case. And this will have a tremendous impact. The assumption that we make about this will have a tremendous impact on the evolution of the system. This plot here shows the fraction of systems that go through stable mass transfer versus unstable mass transfer as a function of the specific angular momentum parameter. And the different lines are the efficiency of accretion. And without going into details, because I don't have time, you see that all these assumptions completely change the fraction of stable versus unstable mass transfer system, and then also the final properties of the black holes. One more thing I want to mention, stellar rotation. All the models I've shown you so far assume the stars do not rotate, which is wrong, especially for massive stars. Rotation, including rotation in the models, has a number of implications. Here I will just mention one thing, which is chemically homogeneous evolution. If a star rotates very fast because of its natal spin or because of tidal spin up or accretion spin up, it may evolve as a chemically homogeneous stars because of effective mixing. But this has many consequences. One is that the radius of the star stays way more compact. And then a binary system may evolve without colliding, even with a short orbital separation. And this produces binary compact objects, especially black holes, with a very different range of properties compared to the standard scenario. For instance, here you see this plot from Pablo Marchand and collaborators, where they show the effective spin that we expect from binary black holes born via chemically homogeneous evolution as a function of the shear mass. And you see that large spin are normal in this case, although not extremely large spins. But there is also this signature in the mass, in the shear mass at around 35 solar masses. So is this possibly connected with the secondary peak of the LIGO Virgo data? Hard to say. Now I will move on to the merge rate density. So in the last 7 minutes of my talk, I will touch upon the merge rate density. This is a huge problem because estimating the merge rate density from the simulations of binary evolution means bridging scales across the entire universe. So we need to interface our simulations of binary stars with what happens at the level of the cosmic star formation rate density and metallicity evolution. This has been done one way or another. The first key ingredient I want to show is the so-called merger efficiency. It is defined as the number of mergers that you have in a coeval stellar population integrated over the lifetime of the universe divided by the initial stellar mass of that population. It gives us an idea of how efficient are the mergers that we expect from that population. And here I show those as a function of the metallicity of the stellar population. You see that for the binary neutron stars, the trend with the metallicity is not the main one. There are other effects that affect the merger efficiency, but they are more connected with the mass transfer, with the stellar evolution theory. For the binary black hole, you see that there is this huge trend with the metallicity. The metal poor binary black holes seem to be 3-4 orders of magnitude more efficient in merging than the binary black holes that come from metal-rich progenitors. And this means that most, if it is true, that most of the mergers that we observe come from low or intermediate metallicities. Now, the implications of this. If this is correct, then almost all the models of binary star evolution predict an excess of the binary black hole merger rate compared with the LIGO and Virgo results. These 4 panels show the predictions for the merger rate density of binary black holes if we change assumptions about binary evolution, and with the different colors if we change assumptions about the cosmic star formation rate density and the metallicity distribution. And the most realistic models are the red and the yellows. The gray line shows the 90% credible interval that we get, that we infer from the LIGO and Virgo data. And you see that all the models, especially the realistic ones, are above the observations. Is there a way to solve this tension? Well, there is one, but maybe it's not the one I like, because as you see from this plot, this is the work by Bursky and collaborators, and they tried all the possible combinations literally. And in this plot here, you see some binary black hole mergers that are still below 100 events per gigaparsec cube per year, still consistent with LIGO and Virgo. But those blue models here assume a very large natal kick, much larger than for the neutron stars, which is possibly not the most realistic one. What about the host galaxies? I will mention a few things about the host galaxies which are particularly relevant for the electromagnetic follow-up. If you still believe that the models are correct, then the situation for the host galaxies seemed to be quite nice, because there were several models from different groups over the years to try to infer the properties of the host galaxies. And almost all of them agree that the merger rate density per, the merger rate, not density, the merger rate per galaxy of binary compact objects scales quite nicely with the galaxy mass, with the stellar mass of the galaxy. Here you see a couple of examples. This is the merger rate per galaxy of binary neutron star, black hole neutron star, and binary black holes. This is the stellar mass of the galaxy at redshift 0. Very nice trend. There is also a very nice trend with the star formation rate density, as you see here and here. But the only galaxy for which we could establish the connection with a binary neutron star merger, NGC 4993, is not forming stars. It is an old galaxy where most of the stars are 10 gigayears old. Is this expected or not? Well, it's kind of expected. For instance, here you see again prediction for the merger rate density as a function of redshift. The black is the total one. The blue is the fraction of the mergers that happen in galaxies with high specific star formation rate. And the red, the fraction that happens in galaxies with low specific star formation rate, like this one. And you see that the blue dominates at all redshift, but at very low redshift. The reason being that now we are well past the peak of the cosmic star formation rate density. And so now most of the mass of the stars is locked up in the most massive, sometimes passive galaxies. So let me briefly mention this plot. Another important thing that we want to learn from the models is the offset. So for binary neutron stars, what is the offset between the place in the galaxy where they form and the place in the galaxy where they merge? And there are some very nice studies that deal with these predictions. The last one was this morning on the archive this morning from Nicola Gaspari, Andrew Levan, and collaborators. So I will jump to my conclusions. I try to convince you that metallicity is a key aspect for binary black hole formation, but maybe not so for binary neutron stars. There are major uncertainties from stellar evolution, especially stellar winds that are being revolutionized right now, core collapse and spare instability supernovae. There are major uncertainties also about binary evolution, mass transfer, and the impact of stellar rotation on binary evolution. The merger rate density of binary black holes seem now to be problematic because we start having strong constraints from the LIGO and Virgo data. And the better we model the synthetic universe, the worse is the excess. The models of host galaxies seem to be nice, but maybe we don't have enough host galaxies to challenge them yet. But the future is bright. I will not go through this slide because I'm late, and Architman already mentioned that the next generation ground-based detectors will do really a great job in improving the sample that we have for comparison with the model. And if you are interested, the Einstein Telescope Blue Book is now on the archive, and you can find there everything you are curious about. So thank you for your attention, and I will be happy to take your questions.
Okay, brilliant. A question before I even asked if there was any questions.
Thanks for the great talk, Michela. I have a question about the scaling of the merger rate with stellar mass. So assuming that there is only one population, if this is calibrated at low redshifts, do you still expect this to hold at high redshifts?
Yeah. Well, this is what we find up to redshift at least 6. And I don't have the plot here, but it's in a paper by Celeste Artale and collaborator 2020, and also this author Chu, Yu, and Lu confirm it. So we do expect this scaling to work well. Of course, up to the cosmic star formation rate density peak, but also a bit after. With some deviation, I can show you the deviations, but the basic idea is the same. Of course, this will not be true when the universe only forms POP3 stars or forms only a few stars. But yeah, it seems to be remarkably good.
Very nice talk, thank you. Actually, because so in your your conclusion slide, so you say that there is a lot of uncertainties on stellar evolution, and there is apparently a big tension in the result. But do you expect that the uncertainties, if you take into account these uncertainties, you will be able to be in better agreement with the observation, or we have to change something?
Great question. Yeah, great question. I don't have the crystal ball right now, but we have a couple of ideas of what could produce this excess. Let me say that the focus of this paper here by Cecilia Sgaletta that was accepted yesterday, the main focus here was to make sure that this problem is not due to the way in which we treat the cosmic star formation rate density and the metallicity evolution. That was one of the claims in the past. So the claim was, oh, but the problem with the rates is that you do not account properly for the metal poor part of star formation at low redshift, because this is where most of the uncertainties are. So here we really accounted for all the possible observational uncertainties, And even in the most optimistic case, we cannot reconcile the merger rate density with the data. So this work at least excludes that the offset could be due to a wrong treatment of the cosmic star formation rate, density evolution, and metallicity evolution. And now we are focusing on the binary evolution side. And we have several ideas. One problem is certainly the common envelope evolution. So this may tell us something about the common envelope evolution, which points in the same direction as other hints like the Gaia black hole. But yeah, I cannot really answer your question fully, but we have ideas of how this could bring the models in the right direction.
Thank you for the really nice talk. So I have two questions following on from the last question about the binary evolution uncertainties. Number one is connected with the natal cake. So you mentioned the core collapse supernovae versus direct collapse. And then are we really sure that in the direct collapse scenario, we really don't get any kicks? And then with the common envelope efficiency, I was wondering how dependent this is on what we assume for the radial expansion of evolved stars. Because at some point the envelope has to engulf. Are those really well understood, and are there major uncertainties there?
Thank you, Ambas, for both questions. So the first one about the natal kicks. No, I'm not sure that in the direct collapse scenario you expect no kicks. Well, actually, you do expect the one from the neutrino loss, but I think that on top of that, there are other uncertainties, and not being a core collapse supernova person myself, I cannot comment on that. Maybe Matteo can tell us more. But connected to the second problem, yeah, indeed, the envelope of a red giant star, when the progenitor is of the black hole is a red giant star, is very loosely bound, can be very loosely bound. And as it was pointed out by several authors, for instance, Rodrigo Fernandez and collaborators in 2018, even a failed supernova can lead to the ejection of the envelope, which is the reason why here there is the pessimistic case in which we only consider the helium core mass as the source of mass for the black hole. And this is pretty annoying because, at least from the stellar evolution side, because when we try to understand whether the real world is more similar to the dotted line or to the solid line, we have to deal with a few models of failed supernovae that help us quantifying this uncertainty literally on the fingers of on one hand. So this is a huge problem. We can kind of come up with some solution based on energetic argument only. So the basic idea is that if the star ends its life as a blue supergiant or a Wolf-Rayet star, you expect its binding energy to be enough, and then the star will not shed further mass. But if it is a yellow supergiant or red supergiant, then I would say that I would personally prefer to stick to the dotted line, but I don't have, I mean, we need help from the core collapse supernova people.
Time for a final question. Oh, good. Then I get one. On the slide 11, let's just on from there.
11.
Yeah.
Okay.
That's the one, yeah. So your black hole mass starts at almost 6 solar masses. Is there a reason why you don't consider black holes with lower mass than that? You feel like they're not secure black holes, or there's some other reason for that?
Oh, it's just the model of core collapse supernova that we are using here. If we do the same with, for instance, delayed supernova model, we would also have lower mass black holes in there. So no, I would say that the cutoff, so the existence of a lower mass gap or the cutoff mass, if there is any, really depends on the assumed core collapse supernova model. And now from the LIGO and Virgo data, we can probably conclude that there is not a completely empty mass gap, but just a dearth of black hole, a lack of black hole in the intermediate range.
And does it make any difference if the black hole mass is a little bit lower? Does that make any difference to the mergers that happen, or nothing at all? Just expect to see that, I don't know, like a longer tail or something like that?
Yeah, but it won't make, I mean, if your question is about will it affect the rest of the curve? Yeah. My answer is no, because simply you move something that is a neutron star in this model, you move them toward the black hole regime. But yeah, this would change if you wanted the rate of binary neutron star and black hole neutron star mergers, but it won't affect these other features.
Thank you. Right. I think we have to move on, otherwise we're going to run over time. Thank you very much, Michela. That was great. Okay. Now our next speaker is Abbas Asghar, who's going to carry on from or evolve from what was just shown. So this is the dynamical formation of compact object binaries.
Okay, good afternoon, everyone. It's really a pleasure to be here, and thank you for the organizers for having me here to talk about this topic. I'm Abbas Asghar. I'm a postdoctoral fellow at the Copernicus Astrophysics